All right, so let's get back since we have how much? And it's 11:30. We have roughly 1 hour 35 minutes. So before the break, we looked at one possible application of IoT and machine learning. So, why is it this guy working? Now let's move on to Industry 4.0, right? I'm going to go quick here. So this term, Industry 4.0, right, was really generated by Germans. So we all hear about German manufacturing, German precision, German engineering, and so on, right? And they are rightfully quite proud of their heritage and their technical abilities in this direction. And they have been thinking about what will be the future industry of the future life, right? So we have all heard about industrial revolution, right? So far, people say that there have been 3 industrial revolutions, and the 4th one, which is coming, is Industry 4.0. So if you go back 1,000 years ago, everything was done by hand. Right? We hardly had machines or something. Things started changing somewhere around 1782, in the late 1700s. And what changed in those days was the invention of the steam engine. So the steam engine was invented, and that started automating many things. So we had the railways, and those looms, right, where you make clothes and so on. They started getting automated and things like that. That was the first industrial revolution. And then the next one was about roughly 150 years ago, or roughly there. And what it was mass production of things now. So instead of making one thing individually, one at a time, we could create thousands of the same product. Right? And what had happened was the electricity was much more, electricity was commercially available now, and the invention of the assembly line. And this was sort of popularized, for example, in the US by this company called Ford. They make cars, right? And previously, if you looked at a car factory, what would happen? The same group of workers, when let's say 4 or 5 workers, they would make the car from the beginning to the end. So they would put the chassis, they would put in the engine, they would put in the wheels, they would put in the hood and the body and everything, and then that's it, right? And people figured out that that's not very efficient. If you give the same job, only one job to a person, so one person will put the chassis and move the car around. It's somebody's job to put in the engine. And that person does only one thing, put in the engine, put in the engine, put in the engine, that's it. And the car moves along, and then the third person's job is to attach the wheels. Right? And that's your assembly line. And that's much more efficient and so on. And then about 1960 to 2010 was the third revolution, and in this case, really, it was the use of semiconductors. Transistors became cheaper, computers became cheaper, right? So now we had that. And the next vision is Industry 4.0, and what the vision here is, some of you may like it, some of you may not like it. It's essentially automating everything. So hardly any humans in the factories anymore. Those of you who are a bit of socialist or leftist in your views may not like it because it will lose, people will lose employment, maybe. That's what many people are worried about. But if you're on the right side, not right in the sense you're right, but and right doesn't mean right wing or whatever. Right means you're more on the capitalist side of things, and you would like it, you would save money and so on. And then the idea here is this. So a factory, you think of this as a cyber physical system. Why physical? Maybe there are robots which are physical things, attaching parts and doing the soldering or attaching wheels, whatever it is, right? And the cyber part is this is controlled through a computer or over a network. Right? And then we talked about IoT, and then there are people who also talk about Internet of Services. If you want a particular service, you go to the internet and get that service, and so on. And all of these will come and make your smart factory. And what this really is, you want a factory to make something, let's say a TV. What needs to be done to make a TV? Maybe there are all kinds of components. They have to be assembled, soldered, put together, and then they're done, right? So what do I need in order to do this? I need all the individual parts to come in. I need a robot which will put the parts in the right place on the PCB. Then I need another robot, or maybe the same robot, which will solder everything together. Then I need another robot which will put everything, the LCD these days, and everything in the back together and put it in the enclosure or whatever box it is in, and then so on, right? So all of these are robots, and these are the physical processes of the soldering part, the assembling part, and so on. And they are being monitored continuously. What is every bit of the robot or this or equipment doing? And all of this is coming into a simulation environment or a virtualization environment. Here you have a piece of software running which allows you to visualize what is happening in every part of your factory. You can see if certain parts are being underutilized or whatever it is, if some certain parts are overloaded. And essentially, this is sort of a simulation environment. All the data is coming in and so on. And you can think, what do I need to do? Or even individually, the robots can think what they need to do. If the same factory is manufacturing both a phone and a TV, there are no TV parts available, switch on to the phone part. Just a very crude example, but you can make these decisions decentralized. A robot can decide what it needs to do. How? You need intelligence. You need data to figure out what's going on. And hopefully you have enough algorithms, you learn enough, you know enough, so you know exactly what to do in different situations. These are the things that will go on. You need autonomous robots, you need data analytics, right? You need augmented reality kind of things which will allow you to visualize what's going on in your factory. You need simulation tools, you need IoT. And even within IoT, right, these days you will see a subfield has emerged. And it's called the industrial IoT or IIoT. That's again becoming a popular word or buzzword if you want to say it that way. I'm okay with it since I have some funding from the Singapore government for that, but anyway. So those things. So IoT specific to the industry is industrial IoT. On the first day of this course, some of you came up towards the end and said, I have a device or a sensor, and it's just connected to a server somewhere within my own lab or something. Is this IoT? This is IoT. That's industrial IoT. Most of the time, the data stays within your factory. It's not being transmitted over the internet to Singapore to me. Right? Everything is within in-house, and it's still IoT. The internet, you shouldn't take it literally to say internet means it has to go through the public internet and then come in. Internet is just a network. You have sensors, they just transmit data. And the things part is, it's not a human generating the data, it's a device generating the data. Right? So this is IoT to me, or to anybody else. Right? And other things, cybersecurity, and these are, if you're in the mechanical engineering kind of space, you will hear this term called additive manufacturing. It's just a fancy way of, well, not necessarily a fancy way, but what this is essentially, previously, how do we make things, right? Let's say I want to make a screw. What do? I start with a cylindrical piece of metal. And then I take a chisel or something, and then I cut off parts of the metal so it looks like a screw now. So that's subtractive manufacturing. So you start with a big thing, and then you cut out parts from it so it looks like. So if you look at how do you make a cricket bat, you start with a big block of wood, and then you chip away at it so that then you have the shape of the cricket bat. Additive manufacturing is the opposite. You start with nothing, and then slowly you do 3D printing to make the shape that you want to get to. And people say this is much more efficient, which to some extent is correct. Right? Because I started with a big block of wood, I chipped away, and I got a smaller bat. What about the rest? Either the rest of the wood is waste, or maybe if I'm good about it, maybe I use it for burning or making plywood or something else. Right? But with additive manufacturing, you only use that much that you need. But anyway. And the kind of things you want is, you want interoperability. So here we have many things, right? We have machines, we have humans, we have the products that we're manufacturing. They should be able to connect and communicate with each other. So that's where you'll have all your information. Then we need to have virtualization. So virtualization says all the factory equipments are there. They're sending me data, and based on the data, I should be able to create a computerized version or a computerized vision of what's happening in the factory. Right? So that's virtualization. And hopefully things are decentralized. I don't need a central facility deciding what's happening in all parts of my factory. Hopefully individual robots can decide what they need to do. Oops, sorry. And it should operate in real time. Things should be modular. It should be service oriented and so on. Right? We don't really care about, so these are more from the part of the factory people. As computer scientists or electrical engineers, we don't care about those things. And this is sort of one way of looking at what, so this is our assembly line, and then there are different robots in different places. And we monitor everything that is going on here. Right? And then at some point we will decide what to do with the data. But here also we need to learn many things. So for example, if I'm manufacturing things here, today or for the next 5 months, my order is this much, next 2 months. How much raw material should I order? When should those components come in? You have to decide, you have to plan, logistics. So a lot of intelligence these days also goes towards planning of all these logistics. Again, like I was saying, storage is very, very wasteful. You only want to buy or get only those things that you need today or you use today. You don't have to worry about this factory thing here, right? You go out of this building, right? You go out, you hit the main road, turn left. You will reach an intersection there. There is a group of kids and I think their father or something, they're sitting there selling newspapers. How many newspapers should he buy? If he buys more newspapers than he can sell, at the end of the day he's going to get a loss. Right? So he needs to know exactly how much he will sell. And ideally that's what he should buy. So it's not just here, right? That person can also use that kind of information. I'm sure he has some idea that every day I sell this, so he has a rough ballpark figure, this much. But essentially what he is doing is, he's doing some kind of intelligence inside his head. But if I'm the newspaper publisher, right? If I'm Times of India or what was it, Dainik Jagran in my days. Is it still there? It's still there, right? That's what we used to get, Dainik Jagran and whatever, Indian Express and Telegraph, whatever, right? If I'm a printing press owner here and I publish those papers, I also need to know how much you're selling, every individual guy, right? So gathering all that information, making sense out of it, it's sort of related here. The other thing which is pretty common in Industry 4.0 you'll hear is predictive maintenance. So right now what people do is, you have regularly scheduled maintenance. Hopefully people actually do their job, right? So in Singapore, which we all think it's so efficient and this and that, last month or maybe 2 months back, there was a lot of rain and one of the tunnels flooded for the metro rail. And the reason it flooded was, so they have equipment to take it. So they know that there will be rains, and when there's rain, water can get in the tunnels. But when that happens, you have to turn on certain pumps. Those pumps will drain the water. And it doesn't rain this heavily every day, right? So what happens is, you don't get to run your pumps every day. Maybe once in 6 months, once in a year. But the pumps are there, and you have to make sure that they work. So there is this maintenance team which goes every month, and they're supposed to check if the pumps are running or not. And if not, they fix it, right? So I don't know what's the situation, but in many places you have to have fire extinguishers now, right? All buildings and corridors, they have to have fire extinguishers. But if you keep the same fire extinguisher there for 3 years, maybe the thing rusts, and when there's real fire, you try to press it and it doesn't work. So test regularly, right? But when you do the testing, for example, in Singapore, these guys were sleeping. They just wrote in their register, I have tested. And when the real rain came, that thing didn't work. We didn't have, on one particular, between two stations, there was no service for 8 or 9 hours. There was a big inquiry. I think 15, 20 people lost their jobs. Whatever, the minister was grilled for it. Whatever, right? But anyway, so there's, and in many cases what happens is our maintenance is reactive. Something breaks down, then I go and fix it. And that's not what we want. And usually what happens here is you have to have a maintenance staff that you maintain in-house, and they have to be very, very specialized and trained to work on the equipment that you work on. So now what it says is we will have online monitoring. So we will be monitoring the pumps or the trains, or in this case these windmills. Anything in general which is moving, has moving parts, is susceptible to breakdown, and which are static, right? So all of these things have lots of sensors and everything which measure every piece of, every gear or other things that what's going on, what's the condition of those things, right? And then they send it. Now, if this particular train, this is a bullet train in Japan, it will probably have a few thousand sensors, maybe more. Am I going, if I give that job to you, you sit there and you look at the sensor data from 1,000 sensors and tell me if we need maintenance. Very difficult for a human to do that. And these sensors are measuring probably 2-3 samples every second. If I give you 1 day's worth of data, it will take a human few days or maybe a month to go through all the data and figure out what's going on. So what do we know? Software-based or algorithms-based analysis. Right? And hopefully, once you analyze, you can tell me what to do. Should I bring in this train for maintenance? If I bring in this train for maintenance, it's expensive for me because the train is not going to run. So I have a cost associated with it. So I only want to bring in that train for maintenance if it is really needed. If your software is crappy, right, then you just say, yeah, bring it in. And that's not right. Okay, questions? Okay. So now let's come to something more network related, right? So let's talk about network self-organization. So what do we want in the future, right? We want consistent, high internet service no matter where I go. Whether I'm outside, whether I'm inside, I just want consistent service. If I'm walking along the corridor here in this room, no matter where I go, it should be the same. How does that happen? And that's not it. This is Wi-Fi inside the room, right? Even if you take a city, we are not using Wi-Fi there anymore. Now we are talking cellular coverage, 4G, 5G, 3G, whatever you want. I want consistent experience no matter where I am. It shouldn't be that, if I'm in the center of the city, it's good, but since I have moved 5 kilometers, 7 kilometers into IIT now, my coverage is not so good. Shouldn't be. So this red dots here sort of tell where the coverage is, right? Ideally, I want it to be uniform everywhere. And if you have a building with many floors, all floors should have coverage. It shouldn't be that only at the top floor or the ground floor, right? So these are complicated things. So I want consistent, and we are going towards gigabit service. That's what 5G promises. Or even in the next generation of Wi-Fi promises gigabit speeds, right? Yeah. And what I want, for example, in the home scenario, the access point that I will get, it will be shipped to me, or I'll just go to the shop or mall and buy it. And I want to just plug it in. And that's it. I don't need to worry about it. I shouldn't have to go and say, okay, if I place the Wi-Fi access point here, things work, if I put it in the corner, what is the optimal location? I don't want to deal with all of this. So what do we do now? There are a number of solutions out there. There are a number of solutions out there, and they're all independent, and their performance varies a lot. Right? And I'll talk more about those things. In the vision is that the network will be self-organizing. At home, maybe your things don't change so much. In my home, there are my wife and 2 kids. That's it. Right? So it's more predictable. But in a building like this, different times of the day, there are different conditions. Or if you're planning a 3G or a 4G network, and you're trying to figure out where to deploy your base stations, conditions are not the same all during the day. Mornings are different, night times are different, office hours are different, right? But hopefully the network will know what to do. It will figure out what is the transmit power. It will figure out what is the frequency I should be using at this point and so on. Right? So the idea is the network should learn and adopt. Right? Network should learn and adopt. No humans should be involved here. So let's see what we do right now. One way is you can go on-site and do a survey. So I can tell whoever provides Wi-Fi connections here or cellular connection here, saying, look, I want, no matter where I am in this building or within the BHU campus or IIT-BHU campus, every place should get 1 Gbps data rates. So what does they do? They bring in some special radio, this is hanging from his shoulder here, and they go around measuring the signal strength everywhere. So you walk every corridor, every road, every floor, and see what it is. And then you have a map of what's going on. And then you have to sort of decide what to do. Should I move this base station from here to here? You need a very experienced engineer to do this. And it's very, very labor intensive. So to do this for IIT-BHU, which is many, many kilometers wide, many buildings, it will at least take for one person, it will take a few months to get this done. So it doesn't work so well. What you can also do is you can go online and buy these planning softwares. So in the planning software, you can create your own floor map. You say, oh, my apartment or my flat has a wall here and then furniture here, beds here and so on. And then it will tell you, okay, where do you want to place the access point? You place it somewhere, then it will tell, okay, if you place the access point here, let's say there are points here, here and here. In this case, they have placed 4 access points. So in the green zones, you have good coverage, for example. Right here we have good coverage, here we have good coverage. But then there are walls here along, so if you're in these rooms, for example, not so much. So you can see what's the impact of placement. This is for a home, you could do it for a cellular network or your IoT network or whatever it is, you could do it. Right? Again, these are dependent on, you have to create the floor maps. And it's not just floor maps, right? It also depends on the propagation model. Propagation model means if I send signal from here, how will it react on the other? How much will I get later on? Depends on many things. So for example, this door is made out of wood. If this was a metal door, it would be very different. In the back there, I think there's a cabinet just behind I forgot his name. Vishal, what's the person's name? The founder, right? Yeah. Madan Mohan Malviya ji. Just behind him, there's a metal cabinet. If you go behind it, probably you won't get any signal because that's a shadowing thing. Right? So it's very, very difficult. If you want a realistic thing, you have to list every bit of furniture, every bit of metal in your house. It doesn't work so much. And then there are other things, right, which you can buy these days. Something called this is from Netgear and OneHub from Google. So one thing, so the idea behind this is an access point. It looks like a cylinder of some kind. And what these guys they say is, why do we put access points in our home in some corner, or in a cabinet or something, or under the TV or something? Because it looks ugly. Right? I don't want to have an access point on my center table. I Most people would want to have, I don't know, flowers or something. So they say, right, we'll have it like this, so it doesn't look so bad. So instead of putting the access point in that corner there, you can put it in the center of the room. So the coverage will be better. But anyway, this is a new thing. So there are some factors which make life difficult for network planning, especially in dense environments. If you're living in a city or in a building like this, one thing is, you're talking about network performance. Ultimately, I want, let's say, consistent gigabit per second network coverage all over. So what impacts this performance? One thing is the impact of neighboring networks. If you live in an apartment complex, right? So if you live in a hostel, maybe a hostel is not a good idea. If you live in a big building and there are flats everywhere in every floor, you have a Wi-Fi network. Your neighbor has a Wi-Fi network, and your Wi-Fi network has to compete with your neighbor's Wi-Fi network. You may do certain things, but your neighbor may react to that, right? And then things become difficult. Right? So as an example, let's say this is your flat, and this is your neighbor's flat. You have put up your access point here, and you try to watch a video while you're sitting in this particular bedroom, let's say. Right? When you are here, you are probably more closer to your neighbor's access point than to yours, and that could potentially create a problem. So what do? You can either move this guy, the access point, somewhere here, or you tell this guy, oh, transmit at a higher power. That's usually what is done. You say, okay, the coverage is not so good, let's increase the transmit power. Because if you think about your home, this is your Wi-Fi access point. Where can you place it? Where the cable connection comes in. Where does the cable connection come in? In some place in your living room. So you are sort of limited. That's the only place I can put my access point. Otherwise, I'll have to run a wire from my living room to my bedroom. I don't want to do that. Take the simple way out. This is where the cable connection is coming. This is where the set-top box is. I'll just put my access point also along with it. So then, if I want coverage here, what do? Increase the transmit power. Right? But what happens if we do that? There is something called the cocktail network effect, or a cocktail effect. So there's a party going on. If this guy can't hear, he tells his friend, talk louder. When he talks louder, the other guy who's in a different conversation cannot hear. So he tells his friend, sorry, I can't hear, you speak louder. So his friend says, okay, I'll talk louder. Now this loud conversation affects their conversation. So he says, oh, you need to shout now. So that's what happens. I increase my transmit power, my neighbor says, oh, now this is, something happened. My neighbor doesn't know what happened. But all of a sudden, one day he says, or she says that, I can't get coverage here. So increase transmit power. I mean, your neighbor probably doesn't go on his or her own and increase, but the base station might do that, access point might do that on its own, right? So then there are problems here. And then there are other things like user experience. If you tell me, you are responsible for figuring out where to put the access point, maybe I can still do it. I'm a networks person, right? You tell my father, well, we don't have an internet connection at home, right? But anyway, my father is 80 years old. You tell him, this is the access point I'm giving you, you figure out where to put it. He's not going to do it. Right? So it's not possible. Asking the user to perform speed tests and then follow certain recommendations like trial and error, put the base station here. The people in this room can do it. I'm quite sure you're capable of doing it. But the general person is not capable of doing it. Right? And if you're thinking of smart homes and other things, who's going to do it? Right? And then this becomes a fairly complicated problem. Then this kind of placements. Should I place it here or here or here? And so on. So what people are sort of going towards is like artificial intelligence or machine learning inspired network planning. And in this case, the main thing is to be cognitive of your environment, to know what's your environment like. So Singapore is fairly dense. So when I used to live in the US, my nearest neighbor maybe 500 meters away. But in more densely populated places like India or let's say Singapore, in Singapore when I turn on my Wi-Fi thing, I can get at least 25 other Wi-Fi networks from my neighbors. So they all create some kind of interference with me, or at least some of them, subset of them. And what I want to do is, this thing should figure out on its own. The user shouldn't have to go and tell that my connection is not good. The access point or whoever it is, the smart agent that is running, should be able to figure out on its own that the user is experiencing bad things, bad data rates. How will it do it? It has to gather some kind of data. For example, we watch YouTube videos, right? You will observe that there are different data rates available with YouTube, or different resolutions, right? If your network speed is not very good, it will switch down to a lower coding rate. And I mean, it will not be as high definition anymore. You'll see granularities and so on. So, as an example, this agent could see that. What is the data rate at which you are watching your video? If it is high enough, then it thinks, okay, the user must be good, must be happy. If it's a low resolution video, then you have to know that, okay, most likely the user is not happy. Right? So the user doesn't necessarily have to put in the preferences or label things on its own. You should be able to learn. And you should be smart enough, right? If I'm watching on a laptop, in general, I would like to watch a high definition thing, right? On this, it wouldn't be. Screen is too small. You give me high definition, it's useless. So when it's this, it's usually on a lower data rate. So this guy should know, is the user watching on a laptop or on a smartphone? I don't have to go and tell it. I shouldn't have to go and tell it, look, I'm watching the video on a smartphone. This guy should know, right? So that's all part of this being environment aware and so on. And learn from all of these things. And it should be autonomous. No input or work from the user of any kind. You figure it out. Right? That's what we're going to. And this is sort of what we will be going towards, right? So the base stations, their first job would be to sense. Sense and figure out, for example, what is the activity around here like. And it's not just my activity, the activity of my neighbors. Right? So figure out everything. Figure out what the environment is, what the demands are like, and so on. And using these, you learn. What are the kind of things you want to learn? You want to learn the user's behavior. What does the user need usually? Personally, for example, I don't watch much videos. My kids watch. Right? They will go on YouTube and watch some cartoons or something like that, right? So ideally, this guy would know that between, let's say, 6 to 7 in the evening, this house watches video. Between 8 to 9 or 10, it's some web browsing of some kind maybe. Right? It has to learn those things. It has to learn the channels on its own. Nobody is going to tell that, okay, there's a wooden thing in between. Right? And it's not just these things which make up the channel. If you are there and the access point is here and people walk in front, you'll have something called multipath fading. It should learn those things, that here there's a lot of multipath fading. In this environment there isn't. And it shouldn't be just mine, it should also look at my neighbors. In my home they watch video from 6 to 7. What is the user demand in my neighbors at that time? And so on. And it can also learn from past. In the past, what did I do? Did I increase the transmit power? Did I switch to a different channel? What was the impact of that? Did it help? In machine learning, this is sort of what is called reinforcement learning. Right? So I look at what I did in the past, and was it useful or not useful? And that hopefully can tell me what I need to do next. Right? So this is sort of a framework of applying learning and intelligence to computer networks and network planning. I guess we talked about these things. All the sensing and building knowledge and so on. We could look at a more specific case of just Wi-Fi, right? And this is something in the United States where people have surveyed. Most of the time, people experience problems. Some halfway there, some attention, but I'm okay with it, it's okay. And about 5% of the time they will say it's no problem. And I don't know if you call up Bharti or whoever it is, your Airtel, I don't know who the common ISPs here are. And I don't know how responsive they are to your complaints. Right? If you call and complain, do they really come and fix it the next day or not? Maybe, maybe not. My parents are at least unhappy with, well, I'm sorry if there's somebody from BSNL here, but their phone is not working probably much more than what they would like. But anyway, so as a company, you don't want people to say these things to you. Right? You don't want that. Then maybe I switch over to a competitor. Right? You don't want that. So how do I do this? Usually there is this thing. We can think of running two loops at the same time. One is to profile, to learn. The concepts are still always the same, right? First you have to learn, and you have to figure out what's going on. Based on what you have learned, you figure out what's wrong. You figure out the diagnostics, what is wrong, what is going on, what is the problem, and then you try to fix it. And this is the simple thing, right? The idea is you gather information, use that information to figure out what's wrong, and then hopefully you can take the correction. But if you dive inside and try to see what's going on, then you will probably, is it 11:30 or what? All right, yes, that's better. I thought it's lunchtime. Right? So if you look at it from a networks engineer perspective, and you would try to understand. So this was very simple, right? I said, look at what's going on and try to figure out what should be done. But then you need some kind of knowledge about what really happens inside the network to make sense of it. And it's your job to make models that will explain what's going on. That's a big part of machine learning. You want to come up with models that explain what's going on. Right? And one way of designing a model that will allow you to model different things is sort of, this is what is called a Markov chain. We don't care about that, but right. So for example, it says if you're on a 5 gigahertz channel here, right, and you use channel number 20 in there, you can get about 108 Mbps. On the other hand, if I use the 2.4 gigahertz band here, and within that I use channel number 11. So the way Wi-Fi works is, within the 2.4 gigahertz you have about 80 megahertz if I'm not mistaken. And then you break it up into smaller bands. And your Wi-Fi access point, and there are 17 such bands I think, in some countries, and 11 bands in some other countries. So your Wi-Fi access point doesn't occupy the entire spectrum. It's on one particular band, and that's what this is. And what it says is, if you switch from this 5 gigahertz band to 2.4 gigahertz band, and you are working on channel 11, you will get 54 Mbps. Why is this channel 11 important? Because you have neighbors. You have neighbors. So why am I getting to, on channel number 11 I get 54 Mbps, but on channel number 6 I get 18 Mbps. It's the same 2.4 gigahertz band. It is related to your environment. Maybe you have neighbors who also have Wi-Fi access points. And maybe there are quite a few of them who are also on channel number 6. So you have interference. But on channel number 11, there are few of your neighbors with the same, operating on the same channel. So this will give you better. In a different environment, maybe this guy will give you 54 and this guy will give you 18. You just need to learn that. You need to collect enough data so that you have a map like this. And now, so from this map, then you figure out different things, right? So you say, okay, I am in this particular channel right now. And let's take an example. Let's say I'm in this particular channel right now. And you have built a map that says, you know, in the evening, when you need higher data rates, my kids are watching videos, maybe my neighbors are still in the office. They don't use their network that much. Then, 6 o'clock, switch over to this particular channel. So you can get higher data rates to watch your video. Just an example, but then you need to build up these models. And it cannot, sometimes you're lucky, it may be simple enough like this. Sometimes your thing might have many more states. Right? But your job is then to create such models, figure out what happens if I go from one state to the other state, what impacts, and then have a logic which says, in this state at this time, what should I do? Should I stay? Should I go to somewhere else? That's the intelligence part of things. Questions?
So which kind of machine learning we can apply for this kind of state management?
If you look at this, so what happens here is this so for those of you who are familiar, this looks like a Markov chain. Right? So I'm in this state, and if I go to this state, I will get this. And usually when you have a chain like this, or states of going from one to the other, and sometimes, you know, there may be probabilities associated with it. It's not guaranteed that if you switch here, you will definitely get, let's go back to the previous example which I was talking. It may be that if you switch from this channel to this channel, it says you're supposed to get 54 Mbps. Maybe this happens only some of the time. Maybe it happens 60% of the time. It doesn't have to happen. What if my neighbors haven't gone to office that day? Right? And they're using their network. So it will create. So most of the time these are probabilistic. There is no hard guarantee. Sometimes there are, if it's a deterministic system, but it could be probabilistic. So in a situation like this, one of the common things that we use is something called a MDP, or a Markov decision process. So you have a Markov decision process. So in this case, what you would do is, first thing, you have to figure out how many states are there. That's your first job. Let it go. You have this many or these many. What are the probabilities? You create those things. Next thing. Here, I'm getting 18 Mbps. Here, I'm getting 54 Mbps. How valuable is this to me? If I was just sending email, right, I don't really care if it is 18 Mbps or 54 Mbps. If I'm just reading news online, I don't care. Right? And what's the cost of going from 18 to 16? Right? Maybe it matters to me, maybe it doesn't matter. But you can also think of this is the Wi-Fi case, right? If you think of a cellular case, this is one base station, the neighbor is another base station. But they both belong to me, I'm Vodafone. I may think, if I go from here to here, these users will get less data rate. But the neighbor, that neighboring cell may get better coverage. So you balance things, right? So what I'm trying to get to is, there is a cost or a reward associated with your action. So in the MDP, you see what are the probabilities, and you see, okay, if I go from here to here, that's my action. What is the cost or the reward associated with that action? And then here I have these many actions. I can either go here, or I can go here, or I can go here. Or maybe, well, I don't have a loop here, but let's say there's a loop here. What should I do? Should I stay or go here, go here, go here? So the MDP has a well-established way of figuring out what's the optimal action to take. Right? So you would solve this MDP and then figure out what you need to do. Okay, so this would fall under reinforcement in that case. Other questions?
Sir, can we classify line of sight signal and null line of sight signal at the receiver with the help of machine learning?
Alright, so the question is, can we figure out if it is line of sight versus non-line of sight? So for those of you who are purely computer science people, let's define what that is. So let's say there is an antenna here. And this is my sender, and this is my receiver here, has another antenna. This is the transmitter. So when it sends the signal, it goes everywhere, right? If there is no obstruction between these two, you will get directly. This is line of sight. In addition, what may happen is some of your rays may hit another building here, let's say, get bounced off, and then reach like this. This one is non-line of sight. In many cases, you may not have any line of sight at all. It's just non-line of sight. Imagine you are inside a building. Right? I'm here. Where is my phone? My phone is here, right? Maybe the base station is on that side. There are walls in between and so on. There is no line of sight with me. Right? So the question is, by machine learning, can I figure out whether it's line of sight or non-line of sight? So in general, I would think that it's there are some things you need to know. What is the transmit power here? If you know what is the transmit power, and if you know what is the distance between these two guys, then you figure out what is the receive power here. If there is line of sight, you expect something. Something of the order of PT 1 over d square, let's say. D is the distance, yeah. Right? If it is non-line of sight, this is the main component, or the strongest component. The reflected waves usually are much smaller. So if the amplitude or the power that you are receiving is much lower, then you can say that this is fine. This is non-line of sight. Things are more complicated if this distance is very, very large. Then the receive power is so small that I'm not very confident if it is line of sight or non-line of sight. Then you have to do some other things. Then you could use, I guess you could use machine learning to see how much is the variation. If there's a line of sight component, usually your power doesn't vary so much. There's a fixed component which is always there. If there's a non-line of sight, then there is something called multipath fading, and that will create ripples in your envelope. So that might be an indication that it is non-line of sight. But then again, you could use other information, like here we were saying you have to use environment. If you're inside the building, your transmitter is outside the building, your problem is solved. It's not line of sight. Right? So if you have that kind of information, just learn from it and then. So, anything else? All right. So now let's come to the last one, which is anomaly detection. Right? And this is fairly broad, and we'll take some examples of what we mean by anomaly detection. And again, coming back to what we were talking about earlier, that there's a large volume of data being generated. And what we need to do is, we need to extract knowledge from here. All kinds of knowledge can be extracted. One specific class of knowledge that we would like to extract is anomalous events. So what's an anomalous event? In general, an event that doesn't occur normally. So normal behavior is this. Something that doesn't conform to normal behavior, that's anomalous, right? Anomalous doesn't necessarily mean it's bad. It could be okay, it could be good even, right? So usually if you look at the sky at night, there are stars. But if you see a shooting star, that could be an anomalous event. Right? We don't usually see a shooting star. But, that's not necessarily a bad thing. But if it is, for example, my trains usually run normally, or my engine runs normally, all of a sudden I see that the temperature of my engine has shot up. That's an anomalous event which is of concern to me. I don't want my engine to overheat. Right? So that's kind of thing. Right. And the problem now, what the picture is trying to show is you have a lot of data and you're trying to find something. And in many cases, for example, this engine overheating or you being subjected to a cyber attack, you have to detect this thing, but you don't have much time. That's why there's a fire on top. Right? And the problem with these things is these make our life in machine learning very, very difficult. In machine learning, the key word is learning. So you want to learn. How do you learn? Usually in the previous example, we say you have observed what's going on. You observe what's going on and then you figure out what's right. But if you have never seen an anomalous event, how will you learn it? And that's one of the fundamental problems in machine learning, specifically to these cases. I'll give you an example either today or tomorrow, depending on how we're doing on time. So definition of anomaly is it's a pattern in the data that usually doesn't occur every day in life. And there are other ways to define the same thing. So for example, outliers. And when we do physics or chemistry experiments in high school, we always worry about outliers, right? Something which doesn't sort of form what I expect, it's too far away, it's an outlier, we just throw it away. And some of the common examples are cyber intrusion, credit card fraud. These are anomalies. If somebody is pretending to be you're using your credit card, that's an anomaly. So these are common examples. One way of visualizing pictorially, and this is useful when we do machine learning and classification and other things, is to see what it means to be an anomaly. So let's say you have data. It has two attributes, X and Y. And these are all the data that you have observed. What you can see is there is this group of data which is all sort of close by. There is another group here. What I would say is, not knowing anything else, I would say that these are normal. This point sort of is in the middle of nowhere. This is an outlier and an anomaly. This has nobody close to it. Looks like it's on its own, must be something special. This is an outlier or an anomaly. Even these 4 or 5 guys, or points rather, they are close by. But they're far away from everybody else. So as a class, I can say that these are anomalies. All the points in this are anomalies. So in machine learning and other places, what your job would be then is to find a line. Maybe that line goes like this. Follow my dot here. So it's a curve like this. That separates the normal from the abnormal. That's one of the basic things we do in machine learning. The best case is if you can have a linear separation. You draw a straight line and that separates the normal from the abnormal. But here, what you can easily see is you cannot draw a single straight line that will accurately classify all the normal and the abnormal. If I draw a line like this, they're normal on either side of the line. I cannot really draw, even if I draw a line like this guy is in the normal class. So you can easily verify that this is, I cannot separate the abnormal and normal with a straight line. In those cases, classification and learning becomes more complicated. We have to have non-linear decision surfaces. And tomorrow and day after tomorrow, we will look at how do we learn these things and how can we classify these things. And things are non-linear. So the main challenge is this, right? So the first thing is, how do you define what's normal? And I'll give you an example. So we're talking about credit card fraud, right? So I usually live in Singapore. Before that, I lived 15 years in the US. So I have credit cards which are American cards. And I usually don't use them. I live in Singapore, so maybe I use them in Singapore. But once in a while, every 2-3 months, let's say I go for a conference in the US. So as far as the credit card company is concerned, what it sees is the card is being used in Singapore. Then all of a sudden, it's been used in Los Angeles, let's say. Anomaly. Right? It's not usual pattern, normal pattern. But is it normal behavior or abnormal behavior? As far as I'm concerned, it's normal behavior. And I get pretty mad at it because I try to use my credit card in the US, it doesn't work. It says your card has been flagged for suspicious activity. Please confirm or call a representative and whatever. So this guy doesn't know that it's abnormal behavior. But I'm still okay with it because, this is 5-6 years back. Somebody stole my credit card information. I think I went to a restaurant somewhere in Florida. Those guys in the restaurant, they stole the card. And they're pretty sophisticated. It's not just the number that they stole and then they could use it online. They created an actual credit card with the magnetic stripe. Nowadays you have a chip on the card, in those days we didn't have it, right? So they actually created a magnetic strip and so on. And some guy, so there's a famous, it's not famous, there's a pretty big shopping chain in the US called Macy's. So this guy was going there and buying TVs worth of $2,000. So he would go buy stuff worth of $4,000 or $5,000. Then somehow go to a chicken restaurant. He would eat his chicken, go back to the mall again. So in one day he bought about $15,000 worth of stuff on my card. Well, luckily these guys caught it, right? So when I go to the US now and then they say your card has been flagged, I don't mind, it's okay. At least it worked sometimes. So the good thing is in the US when this happens, it's okay, I don't have to pay anything. So the credit card absorbs everything. I don't know how it is here. In Singapore, the credit card company will say it's your job, it's your problem. Why did you let your card being stolen? US is nice in that sense. Fine. So that's the reason I still keep the US card, even though I don't live there anymore. But anyway, so the thing is, normal and abnormal, defining that is very, very difficult. And the boundary between normal and abnormal is often not so precise, right? If I believe that this is normal and this is definitely abnormal, right? So this is normal, this is abnormal. And I want to draw a line that separates the normal class and the abnormal class. Somehow I can't draw in here. If I could use my own laptop, I would draw, but imagine that, right? So should the line be here or here? Let's use a board. I don't like waving my finger. So this is what it is. Let's say this is my normal, and I have a point here which is abnormal. And now my job is to draw a line that classifies it. So where should that line be? Here, or here, or somewhere here. All of those lines work. But which is the right line? I don't know, right? So the boundary between abnormal and normal may not always be very precise. That's one problem. Also, what is normal today, or what is abnormal today, may be normal tomorrow. Right? So things change with time. So we don't know exactly what's happening. And again, you develop one algorithm for one particular scenario. You say, okay, this I did for smart grids. Now I can detect anomalies in smart grids. You apply it to a transportation system, do you think it will work? Most likely it will not work. Right? So this thing keeps changing. And the other thing is the availability of labeled data. If I want to make this diagram here, right? If I say that this is the abnormal class, this is the normal class, somebody has to first come and verify. This is really abnormal, this is really normal. Most of the time for us, for data scientists, you would get smart grid data. Or if you're trying to detect tumors from ultrasound images, you can get lots of ultrasound images. But is that white thing that you see in the corner, is that a tumor or not? Who can tell it? A real doctor, right? A specialist. Are you going to go and ask a specialist, please label this for me? Most of the specialists will say, I have better things to do. I have real patients who are dying, I would rather go and attend to them than label your figures for you. Right? So, where did that figure go again? So the availability of labeled data is very, very difficult. That's one. And then, let's say you are doing this for security or something, right? You want to see, okay, if this happens means an attack, if this means this is a normal. The attacker is not stupid either. The attacker knows these days that you're probably using machine learning. And you're trying to learn behavior. So what the attackers will do now is, they will try to fool your learning too. The attacker will put in data of its own. So that normally you would think that, oh, this is normal behavior. It will put in data, or it will start sending data packets which don't do anything. You'll see that, okay, a packet is coming from this IP address. It didn't do anything, it's fine. It's fine. You observe that data packet coming from a certain IP address to a certain port number, and even it's fine. So your learning says that this particular host can be trusted. But one day when it wants to attack, it will send a malicious payload. But your firewall or whatever it is, it will allow it because you have learned that it is okay. Right? So this is called adversarial machine learning. I know that you do these things. I know you do these things, or I know that your machine learning algorithm looks at these features. Then I will use a feature which your machine learning algorithm doesn't look at. Right? So if you go to the airport security, you observe that this is what happened to me on Thursday when I was coming here. Right? So here in India, you have to go and then stand and then they will pat you down, right? Pat you down. This time, or the last couple of times when I saw is, they didn't do this. So to me, the features they are looking for are arms, stomach or whatever, and the thigh. I know that they're supposed to check everywhere, right? But assume that this is what they do, arms, thighs, and so on. Now, as an adversary, I know what is your machine learning algorithm like. You don't check this. So I'll put my whatever gun or whatever it is down there. Right? So that's another way of in which a machine learning algorithm can be exploited. But the most common one when we say adversarial, it is the fact that the adversary is changing the training data or feeding you mislabeled training data. So you think abnormal things are normal. Right? So that's what happens. And then the data might contain noise. Right? You don't always get the exact data. It may have noise, and because of noise, this might have gone up here. Maybe this is a really a normal case, but because of noise in the measurement, it went up here. So how do you know? And in terms of, so we'll talk about these in more detail. So the aspects here are, so you have to worry about what kind of input data is there. Do we have supervision or not? We'll talk more about this and what kind of anomaly it is and what kind of output we're expecting and so on, and how we evaluate it. And these are all very, very related to machine learning, so I'm going to spend a little bit more time on this. Right. So what about input data? Okay. Most common form of data that we have is what is called record data. Records of events that have happened. So in the example that we were doing yesterday, or the case that we were studying yesterday, are firewalls, right? If you have a firewall, what we were doing yesterday is we'll look at every packet and then we'll decide what to do. What the firewall also does is, it keeps a log. It says a packet from this IP address came for this IP address. And this was the port number, and this was the number of bytes in that packet. And you could have many, many more things. What time it came in. I have only one port here, you could have the source port also. You could have protocol fields, whatever, right? You have records like this. In some cases, it could be univariate, so only one variable, so only the IP address maybe. But most of the time, this is multivariate, so there are multiple variables here. And hopefully in the end, you have a label that says what class it belongs to. Was it attack or was it not an attack? Right? So our data would usually look like this, most of the cases. And then, for each of these variables that I have, they may mean many different things. They could be, their attributes could be different. So for example, in this case, this is a binary variable, yes or no. Some cases it could be a continuous variable. Time, what time did it came in, or duration, how long did it last. So this is a continuous. In some cases it could be categorical or integers or continuous, whatever it is. These are some of the things. Binary, categorical, continuous, sometimes even hybrid and so on. Was there a question? No. Right. The next thing is the data labels. How do I know if it belongs to anomaly or normal? Somebody has to do the labeling for me. And based on whether labels are available or not, you come up with different kinds of machine learning techniques. If you have labels available, so for example here, I had labels available. Is it attack or not an attack? So every piece of data that I have as input to train my system already has a label. So I know, so there's some expert somewhere or some teacher somewhere who knows everything. Is it an attack or is it not an attack? So your data is labeled. When this thing is available, this is what I call supervised learning or supervised anomaly detection. Right? So you know what I'm saying. In some cases, life may be a bit more challenging. You only have labels for some of your data. You have a lot of data, but labels are available for only a subset maybe. Or you have labels available for only a subclass. There may be packets here, for example. In this, so imagine I only know if it is a no. If it's a suspicious packet, I just leave that field open. I don't know what that is. In some cases, I can be definitely sure that it was not an attack. Right? Maybe I know because I sent that packet or my friend sent that packet. Right? In some cases, it is possible to be sure. In that case, I can put that label. In some, I don't know, maybe this was an attack, maybe this was not an attack. Maybe it was just some random event that happened. Right? I see a packet coming all the way from Mongolia. Is it attack or is it just some guy in Mongolia was curious about IIT-BHU? Who knows? Right? I cannot put a label there. So I leave it open. So that's semi-supervised learning. And in some cases, I don't have any labels at all. That's the worst case in some ways. You don't have any labels at all. In this case, it's completely unsupervised. And here I'm saying anomaly detection, anomaly detection, anomaly detection, but these are also machine learning. You could also replace anomaly detection by machine learning and say this is how unsupervised machine learning works. And there are no labels here. And still we need to learn, we need to classify, we need to figure out what to do. And what are the anomalies like? Here I just had, this is the normal, and that is the anomalous region. But anomalies can again be different kinds. So for example, we could have point anomalies, contextual anomalies, or collective anomalies. Let's look at those and see what it is. This was an example of a point anomaly. Right? So, an individual data instance is anomalous with respect to the rest. So this guy is anomalous with respect to the rest. Why? Because it really is too far away. It doesn't belong here. So I can say that one particular instance is anomalous. Right? In this room, everybody is of Indian origin, I guess. Right? If there was a Chinese person, you could say that's an anomaly. It's a point anomaly. That one particular person doesn't fit in with this group. And that's what it would be. What I could also say is contextual anomaly. So let's look at this data here, which shows the temperature. Right, which shows the temperature for different months. And the data goes like this. I don't think this is, I guess this is something in the northern hemisphere. So during the summer months, the thing goes up, and in the winter it goes down. Now there is this data point here. I say that this is an anomaly. But there is another data point here with the same value. That's not an anomaly. Right? So just by looking at the value, in the previous case I just looked at the value. The value said you're something else. And I said you're an anomaly. But here, just by looking at these two values, they're the same. So why is this an anomaly and this is not an anomaly? I look at the context. I see that this was in the middle of the summer, right? This is June. All across, all around it, the temperature is high, and you're all of a sudden telling me that the temperature is low. So that's an anomaly. But in this case, the temperature is low, but I know that by looking at the rest of the data around or whatever it is, I know that this is winter. So in the winter, I expect low temperature. In the summer, I don't expect a low temperature like this. So that's contextual. In the context of weather information or time information or seasonal information, that's an anomaly. Okay? Then there could be collective anomalies. Right? And in this case, we are looking at a collection of related data, not just one data point. In both the previous examples, I was looking at a specific data point. Here, not one, but I look over either a period of time or over a given geographical region. So there's a collective thing, right? In this case, here, collectively, I should see a spike like this, then goes down. This is sort of a heartbeat, heart.
Time series kind of thing.
It's a time series thing. And there is a pattern here, right? It should go up, go down, and then something like this. All of a sudden, there is nothing here. So I know that there is something missing. In a sequence, I was expecting to see like this, but I don't have it. So this is your third kind of anomaly, whereas a collective anomaly. So you look at sequential data, either in time, or you could look at space. You say, all the sensors in this building are suddenly reporting 0. So then you say, something must be wrong, cannot be. Right? And then what should be output of this anomaly detection thing? What do we get as the output? Right? In some cases, we can get a label saying yes or no, attack, non-attack, right? And this is when we are doing classification-based approach. So we classify anomaly, non-anomaly, normal, abnormal. Right? And in some cases, we don't really know for sure. So I can say is, I will give you a number, let's say between 0 and 1. If I give you 0.8, that means I'm not really sure, I'm not 100% sure that this is an attack or an anomaly, but I think it looks like an attack, right? It gives me some kind of confidence. It tells you what's my confidence level. So with 80% confidence, roughly speaking, I think it's an anomaly, right? So then you can rank it. And then maybe you can put a threshold somewhere. If your output value is more than 0.75, then it should be an attack. Or if it is more than 0.5, whatever it is. How do you select that threshold? Answer is nobody knows, but might depend on your specific case. Fine. So we know what the output should be. Now you have class. You are detecting anomalies, and you are either giving me a class saying it's an anomaly or not an anomaly, or you are giving me a score. How do I know how good or bad is your algorithm? Right? Finally, whenever you have developed something, we have to test it, right? To evaluate it as good or bad. So how do we evaluate these things? The way you would evaluate it is something called a confusion matrix. Right? So imagine all your data. There are only two classes, let's imagine. Normal, that's NC, or anomalous, which is C. Right? So you have two. Now, in your real data, you have so many data points. But they're either normal or abnormal. And every data point that you see, then you classify. You classify them as either normal or not normal. So if you have 100 such data points, these should add up to 100. Right? Let's say you have 100 data points. This one says how many were really actual. How many were really normal. This one. How many were really normal and you got it right. You classified it as normal. This one says how many were really normal but you classified as abnormal. So this gives an indication of false positive. Right? This one was really abnormal, but you said it's normal. So that's wrong. And what kind of wrong is it? Negative. Right? It's a false negative. Because you are saying it's normal. It's not normal. So it's a negative. This was a positive because you made a mistake. What kind of mistake? You labeled it as positive or abnormal. And in this case, what it is this is abnormal, and you also label it correctly. So this is a true positive, TP, true positive, right? And this is true negative. Now what you would say is, all right, how should I evaluate the accuracy of my classifier? What you could say is, okay, let's look at the accuracy. What is the accuracy? Accuracy says this plus this. This is my accurate ones, right? TP plus TN, that's when I was accurate, divided by the total number of samples. That's accuracy. But it turns out that that's not necessarily a good way of measuring what you're doing. These are all statistical tests of how your classification is working.
System performance.
It is system performance. But the thing is, if I just use accuracy, how many did you correctly classify? Let's say my anomalies are very, very rare. Right? Most of the time, everything is normal. And only 1 in 1,000, it's abnormal. Right? 1 in 1,000 is abnormal. I have to classify it. I will come up with a very, very simple and trivial classifier. My classification rule is everything is normal. That's my classification rule. I don't look at anything. This is not very, what are you doing? But this is a valid classifier. As a classifier, it's a classifier. It says everything is normal. Now you evaluate its accuracy. How well did it perform? Let's see how it did it perform. I had 1,000 samples. Right? What I will say is everything is normal. Right? And how many were really normal? Let's say 999 were really normal. And 1 was abnormal. Right? And in this case, what will be my accuracy? I classified 999 correctly. Right? So my accuracy is 999 over 1,000 samples. 99.9% accuracy. So this classifier is 9, but this is a crazy classifier, right? Doesn't make any sense. You just labeled everything normal, and I got lucky because the data is such that it's okay. So the way we should be evaluating is there are many ways, and people can argue all day, all night about what is right and what is wrong. But one of the things people use is something called the F measure. And the way we will do this, so this is recall.